In this video, we're going to have the opportunity to start zooming in and focus on properties such as temperature and pressure on more of a molecular scale, and how this microscopic scale can help us understand the macroscopic properties that we experience every day. So today, our focus is on something called kinetic molecular theory, or on shorthand, KMT. So to first start talking about this, there are some assumptions that we're going to need to know when we talk about kinetic molecular theory in terms of gases and what makes an ideal gas. Our first assumption is that we are dealing with a large number of identical molecules, that if it's a tiny number of these, it's not going to provide the same properties that average out in the scale of large numbers. We also are going to assume that the volume of the molecules themselves is negligible, that most of the space in a gas is empty space, that the molecules are very far apart from each other, atomically speaking, and the volume of them themselves, each atom or molecule, is not going to be a major part of the volume in which they are bound. The motion is random, so there is not say an electric field that is pushing them in one direction or the other because of that charge. And there are no forces that are acting between molecules. This is also part of the fact that they are far enough apart that there are no intermolecular forces that are changing how they're moving. That would make them act more like a liquid than a gas. And then finally, all collisions should be elastic. If you remember back to our conversation of momentum several units ago, elastic just means that the kinetic energy is conserved. This is one of the few times in nature that we actually see true elastic collisions. Most of the time, some of that kinetic energy is lost to heat or some other forms of energy and doesn't stay kinetic energy the entire time. Well, in an elastic collision, the kinetic energy is conserved. So if a molecule hits a wall, it bounces back at the exact same speed, just in the opposite direction. All of these assumptions are true when we have what we call an ideal gas. We'll talk later on about ideal gases and things that make them not ideal anymore. And the primary thing that we could see that would make these a non-ideal gas is if we compress them or change their temperature dramatically so that these molecules start to slow down or become really close to each other. But right now, we're going to assume that all of our examples today are dealing with ideal gases. And truly, this kinetic theory is all about these molecules in motion and colliding against things. If you have a ball, for instance, hitting a wall at 8 meters per second and bounces back at negative 8 meters per second, we can figure out the force of the ball on that wall because it's an object in motion colliding with a wall. We would just use our impulse and momentum sort of relationship. If you remember, impulse is force times the change in time, the time that the ball in this case is in contact with the wall, that is going to equal to its change in momentum. Well, if we know that the mass of the ball is 5 kilograms and the duration of time that the collision takes place is about 0.2 of a second, we can figure out the rest by noticing that the change in velocity is 16 meters per second instead of being 8 or 0 in this case. It stops and then speeds up in the other direction 8 meters per second with a difference of 16. I can rearrange this equation to solve for the force. That's just the change in momentum divided by the change in time. Change in momentum is just the mass times the change in velocity, that's 16. So plugging in the values that I know, I can find that the force of this ball on the wall is about 400 newtons. And likewise, the force of the wall on the ball is 400 newtons, just in the opposite direction. Molecules work like this as well. In this case, this is an elastic collision because 8 meters per second in results in 8 meters per second out. Kinetic energy before and after is exactly the same. Imagine this on a tiny scale with thousands, millions, billions of molecules that are moving around and bouncing off container. This is going to give you pressure. So if molecules are colliding with the size of a container, that is what we think of as pressure. If you blow up a balloon, the reason it's able to stay inflated is the pressure of the air inside. And the pressure comes from the molecules physically bouncing off the balloon and kind of pushing it away. We can define pressure mathematically as just force divided by area. It's how much force is being acted on a certain given area of the wall or the balloon or anything else that you're measuring the pressure on. So the force we're going to represent with a capital F, units of newtons, as we have before. Area is a squared quantity measured in meters squared, which then means pressure, our lowercase p, is just newtons per square meter. There is a derived unit to allow us to talk about this a little bit easier, and that is known as the Pascal. So abbreviated capital P, lowercase a. The Pascal is just equivalent to a newton per square meter. Which brings me to one of my favorite jokes. Einstein, Newton, and Pascal were playing hide and seek with each other. Einstein was up to be the finder, so he closes his eyes, starts counting. As he's counting, Pascal goes and hides, but Newton just hangs around here right in front of Einstein, just takes out a piece of chalk, draws a little square on the ground underneath him. Einstein stops counting, opens up his eyes, and sees Newton standing right there. He says, "Newton, you're terrible at this game. You were supposed to hide." And Newton says, "No, you didn't find Newton. You found a newton per square meter. You found Pascal." All right, so units of pressure. There are many different units of pressure besides the Pascal that you can actually use to measure the pressure of a gas. One is atmospheres. You may have seen this in a chemistry class. Our atmospheric pressure is 1 atm, 1 atmosphere of pressure. In pascals, that's equivalent to about 101,000 pascals, which seems like a huge number, and we'll talk about that in a little bit. This often is approximated to 100 kilopascals. That's a pretty nice approximation. That's fairly easy to remember. So 100 kilopascals is the same thing as 100,000 pascals, which is about 1 atmosphere. You may also see units of torr. 1 atmosphere is about 760 torr, which derives from measurement tools that actually use mercury in a tube, and the displacement of the mercury, the liquid mercury in there, is 760 millimeters if it's under 1 atmosphere of pressure. So you'll see a variety of different units. Most of the time we're going to use pascals in here. Sometimes you'll use atmospheres, as long as atmospheres is consistent throughout. So if we think about this huge number of pascals when we talk about atmospheric pressure, sometimes if you've ever experienced a suction cup and the force that allows a suction cup to stay on, or if you have like a doormat that doesn't have any leaking holes, it can be fully seated against a surface, you have a lot of atmospheric pressure that you can actually feel as a force. So here this doormat has dimensions of 0.76 meters in one way and 0.43 meters in the other direction, which gives us a square area of 0.33 meters squared. I can figure out the force of the air pressure pushing down on this, knowing now its area. Remember, if you know the atmospheric pressure, which is about 100 kilopascals, or 101,325 newtons per square meter, that's the definition of Pascal. This is 0.33 squared meters, so I can multiply those together to find that this doormat is experiencing 33,000 newtons of force pushing down on it. Earlier in this class, I used apples as my reference point for how big a newton is. 1 apple sitting on your hand is exerting about 1 newton of gravitational force on your hand. Imagine trying to hold up 33,000 apples. It's a huge amount of force of atmosphere acting, and most of the time we don't feel it because atmosphere pressure is acting on all sides. So I'm not feeling that sort of pressure if I hold out my hand because atmosphere is pushing on both sides of my hand equally. But if you create a vacuum on one side, it is really a really huge amount of force that atmospheric pressure is pushing with. All right, let's shift gears a little bit and talk about this kinetic molecular theory, these molecules in motion, and what that has to do with temperature. We've alluded to this before, that temperature, a measure of how hot or cold something feels, is really just a measurement of the average kinetic energy of the molecules in a substance. So it's like figuring out their speed, and we're actually going to do that here in just a little bit. Our temperature scales that we've talked about, mainly in this class, are Celsius and Kelvin. Well, this Kelvin scale has a 0 point that is very much related to the molecules that are there. If you remember, Kelvin is arranged so that 0 is the coldest possible temperature when the molecules stop moving. So in kinetic molecular theory, we are really going to like using Kelvin because its 0 point makes a lot of sense with the molecule's motion. Because of that, we're going to call Kelvin the absolute temperature. Absolute referencing no motion at all for our molecules at 0. So with our absolute temperature, we can actually calculate the kinetic energy. We've talked about the fact that temperature is a measurement of the average kinetic energy, but we didn't talk about how to quantify that and actually calculate an exact kinetic energy from it. Well, this equation, this mathematical relationship, is going to allow us to do that. EK bar, we'll talk about that bar in a second, is equal to 3/2 kBT. This kB is a constant that shows up in your data booklet. kB is known as Boltzmann's constant, which is equivalent to 1.38 times 10 to the negative 23rd joules per Kelvin. This 10 to the negative 23rd, you might recognize 23 as an exponent from your chemistry days. We'll talk about why that is familiar later on in this unit. That isn't random that the 23 shows up here, but this is Boltzmann constant. You will always be given this. You do not need to memorize it or anything like that. Then the other two variables that show up here are this average kinetic energy that we call EK bar. This bar is a mathematical symbol that represents the mean or the average. So when you draw that bar over the top of something, that tells you that you're taking the average of it. So it's representing the average kinetic energy in joules is what we're calculating here. And the absolute temperature is a capital T. When we see capital T and it isn't a change in T, we have to use Kelvin. Absolute temperature will not accept Celsius because 0 point in Celsius is just when water freezes. That has nothing really to do with just molecular motion, so that is not our absolute temperature scale. To see this in the IB Physics data booklet, we can see the pressure equation that we talked about earlier shows up in subtopic 3.2, as well as this kinetic energy equation showing up here towards the bottom of 3.2. KB, Boltzmann's constant, shows up in our list of constants and variables at the very front of the data booklet. Let's look at an example here to talk through some of the things that you're going to have to be aware of when you're calculating this kinetic energy of the molecules. If you're given an example like this, calculate the average translational kinetic energy of molecules in air at 27 degrees Celsius. Well, what we're going to need, we'll need Boltzmann's constant. We're going to need the temperature. Temperature that's given here is 27 degrees Celsius, but that is not absolute temperature. That's in Celsius, not Kelvin. So to convert that into Kelvin, we're just going to add 273, which will give us a total of 300 degrees Kelvin that's going on here. Our equation that we saw earlier was 3/2 kBT. So now it's just as simple as plugging in our numbers. So 3/2 times the Boltzmann constant, 1.38 times 10 to the negative 23rd, times our temperature in Kelvin, 300, will give us an average kinetic energy of 6.21 times 10 to the negative 21 joules, which seems just like a silly small amount of energy. And that shouldn't be surprising because that's the average kinetic energy of a single molecule. And one molecule isn't going to have a lot of mass, so it's not going to have a ton of energy individually, but you add up all the molecules that there are in the gas and your energy increases substantially. This is the average for a single molecule. So to translate that into a single molecule and how fast it's moving, we need to remember back to our conversation of kinetic energy earlier this year. Kinetic energy, we looked at here, can also be solved in terms of the mass and velocity of the thing that is moving. So 1/2 times the mass times the velocity squared will also calculate kinetic energy, assuming that we have some average velocity or speed that we're dealing with here. With that in mind, we can actually relate these two equations together, that they are equivalent to each other, and we can use one to calculate the other. If I want to know the average speed, how fast an oxygen molecule is moving, at 0 degrees Celsius, the freezing point of water, we can actually calculate that speed as long as we know the mass of an oxygen molecule. Here, I have EK bar is 3/2 kBt, but that's also equal to 1/2 mv squared. That's the same kinetic energy. We're just relating these two equations that we found in different units of our year. Everything here is known except for the velocity. We know that the mass of the oxygen molecule is 5.32 times 10 to the negative 26 kilograms. We know that our Boltzmann constant is 1.38 times 10 to the negative 23rd. We know that the temperature is 0 degrees Celsius converted to Kelvin is 273 Kelvin, which means that I can plug all of that into this equation. 3/2 times kb times t is equal to 1/2 mv squared. Solving for the kinetic energy, that is a pretty small kinetic energy, 5.62 times 10 to the negative 21, but it's a tiny mass, which means that if I solve this for the velocity, multiply both sides by 2, divide both sides by the mass of an oxygen molecule, and then take the square root, I get a velocity of about 461 meters per second. That's really, really fast, faster than the speed of sound. But that is our average speed for an oxygen molecule at the freezing point of water. If it gets hotter, we are going to speed up that oxygen molecule. If it gets slower, that means it's going to be colder. But we can use the mass, the temperature, to calculate how fast these molecules are going, which just blows me away. I find that to be beautiful and fascinating, that with a very simple relationship, we can calculate something that you can't see with your naked eye. So all of this leads to just a conceptual comparison that you should be able to make. If I have hydrogen gas, H2, at 23 degrees Celsius, about room temperature, and oxygen gas at 23 degrees Celsius, they both have the same temperature, which molecules are going to move faster? You should know from your chemistry days that hydrogen is the lightest element that there is. It is lighter than oxygen. If both of these are the same temperature, then hydrogen is going to be moving faster. And here's why. Both of these at the same temperature are going to have the same average kinetic energy, because 3/2 kBt, the only thing in there that matters is this 23 degrees Celsius. Convert that into Kelvin, and both of these are going to have the same average kinetic energy. But if they have different masses, their velocities have to be different. If you have a lower mass, in order to get the same kinetic energy, you have to have a greater velocity. So if the mass has the same kinetic energy or temperature, the lighter one will always be moving faster, because the only way for it to have that much kinetic energy is by just moving faster. That's how it makes up for the fact that it's lighter overall. So the takeaways from this lesson: you should be able to describe the conditions necessary for a substance to be considered an ideal gas, that list of assumptions that we talked about at the beginning. You should be able to define pressure with fundamental and derived units of newtons per square meter, which we use as pascals. You should be able to relate average molecular kinetic energy with the absolute temperature, using that 3/2 kBt relationship, and then use that to calculate the average molecule speed if you know the temperature and the mass of that molecule. And then ultimately conceptually compare: if the mass is lighter, then the velocity has to be greater at that temperature to have the same kinetic energy.